Hello, everyone. My name is Robert Howell, and I'm an engineer in the professional development at ACI. I'd like to welcome you to today's webinar, part of our Constructability series, Design and Detailing Steel Reinforced Concrete Structural Members for Constructability, Columns, Walls, and Foundations. We're glad that you could join us. A PDF of the presentation you're about to see can be found in the handout box. You can use the PDF to follow the presentation and take notes if you like. Note that this is a 90-minute presentation. Please note we are presenting this webinar as part of our Constructability series. This webinar is a third of 6 webinars that ACI will present within this month and next month regarding constructability in concrete design and construction. It is planned that this is a Constructability series will be developed into a certificate program, joining others that ACI offers. More information will be forthcoming on our website. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1.5 PDH. Your certificate will be available in the ACI University under the Certificates tab within 2 days. For those who cannot join us live, an on-demand recording will be made available about a week after the live presentation. You may ask questions using the question box in the GoToWebinar software. Our speaker will be happy to address questions at the end of the presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1.5 learning units. This webinar will provide guidelines on how to design, size, and detail steel reinforced, cast-in-place concrete columns, walls, and foundations in building structures, and this will result in enhanced constructability of the structure. Our learning objectives for this webinar are shown on the screen and in your handout. And now I'd like to introduce today's speaker. David Fenella is the Senior Director of Engineering at the Concrete Reinforcing Steel Institute. He has 30 years of experience in the design of a variety of buildings and other structures. David has authored numerous technical publications and is a member of several ACI committees. He also serves on ASC 7 committee, the Committee for Minimum Design Loads for Buildings and Other Structures. David is a fellow of American Concrete Institute. He's also a fellow of American Society of Civil Engineers, ASCE, and the Structural Engineering Institute, SEI. In 2014, David received the Alfred E. Lindau Award from the American Concrete Institute for outstanding contributions to reinforced concrete design practice. David is a licensed structural and professional engineer in Illinois and is a past board member and president of the Structural Engineering Associations of Illinois. And now David will begin today's presentation.
Thank you, Robert, for that introduction, and I welcome everyone to our second session on this constructability series for the design and detailing of reinforced concrete structural elements. So similar to what we did yesterday, we would like to look at some specific reinforced concrete elements, columns, walls, and foundations in this second session. We're going to start by reminding ourselves what constructability is, especially with respect to steel reinforced concrete structures, and then go in depth for these different structural elements for the columns, walls, and foundations. And as Robert had mentioned, we're going to talk about how to size these, how to design them, and how to detail them, keeping in mind constructability during the entire session. So we're also going to include tolerance compatibility, because that's a very important and integral part of making sure constructability is satisfied. So given that brief introduction, we'd like to now get into our first topic, which is our general overview of what is constructability. During the first session, I put this slide up here. This is the definition from the Construction Industry Institute. Optimal use of construction knowledge and experience in planning, design, procurement, and field operations to achieve overall project objectives. And like I had mentioned yesterday, This is what we are striving for in a steel reinforced concrete project. The ability to easily construct the formwork, the ability to effectively install the reinforcing bars, and making sure that the concrete is placed properly without honeycombing or any other issue during the overall construction process. So we're going to start with columns. We're going to take a look at how to size them, how to design and detail them, keeping in mind these three important elements of constructability. So, determining a preliminary column size. As we know, we have different types of transverse reinforcement that we can provide in a column. Ties are certainly popular. Spirals are popular in some conditions. One of the constructability issues, as I'm sure you're aware with the spiral column, is that when we have a joint, especially with beams coming through that joint, we can have an issue with the longitudinal reinforcement interfering with the spirals, especially for the very tightly wound spirals, 2.5 inches on center. So keeping that in mind, these are the different types of transverse reinforcement, and we'll talk about that in more detail in a few minutes here. But in terms of a preliminary column size for those different types, it's always best from a constructability standpoint to use a low percentage of longitudinal reinforcement. That's going to give us a lot more space, especially in the joints, for the longitudinal bars in the column and the beam to pass with minimal types of congestion. Now, ACI 318 does not give minimum cross-sectional dimensions for columns in buildings assigned to seismic design category A through C. Basically, providing anything less than 10 inches in those seismic design categories is going to result in something that's not constructible. And I don't think, anyone would use something that small, even for, relatively very small loads. Having something less than 10 inches, you can imagine, even providing ties in something like that is going to be challenging. So from an overall constructability perspective, 10 inches is the bare minimum. We would certainly recommend 12 inches or above in order to come up with a constructible construction of those columns. Now, we're not covering seismic per se in our sessions, our two sessions, but there are minimum dimensions if the column is part of a special moment frame, which, as you know, is required in seismic design category D and higher. They do give a minimum cross-section dimension of 10 inches. That's one of the requirements. Now, if you have a special moment frame, it's really, really unlikely that you're going to use something that small, especially if you assign only a few number of frames to the seismic force resisting system. So yes, they do give you a minimum dimension, but you're going to wind up with a fairly significant column, especially if the column is within a limited amount of frames resisting the seismic load effects. So summarizing here, low percentage of longitudinal reinforcement to help in relieving congestion, especially at the joints. You'll see I always put fire resistance here. That certainly comes into play, but again, if you're sizing these columns for strength, very rarely are you going to run into any issues with a fire resistance rating of 2 hours or so. Even if extreme cases, providing the minimum column dimensions for strength is going to get you even much more than that. So we list it here because, of course, it's an important aspect that needs to be considered, usually satisfied, though, according to the code requirements. So we say limit the amount of longitudinal steel in the column. Well, what is that upper limit? If at all possible, it would be great to limit the amount of longitudinal reinforcement, which is the area of that longitudinal reinforcement divided by the gross area of the column, to 2%. As we know, concrete resists axial compressive loads much more effectively than any type of steel reinforcement. So having more concrete there certainly makes sense. And limiting it to 2% is going to help out a lot with constructability, especially at the joints, and especially if you're going to use the typical type of splice, which is a lap splice right above the floor level. That area can get congested very, very quickly. And just to give you a real simple idea of what that is, when you're using lap splices and you're lap splicing all the bars at one particular region of the column, and that of course is by far the most common thing to do, you can run into issues very quickly once you have 3-4% of reinforcement in the column. So what we've illustrated here on the left is a typical column with bars around the perimeter, which are your main reinforcing bars, longitudinal bars for the column. And then these other bars that are on the inside are depicting what the bars are either above or below that particular section at the lap splice. So you can see for this situation, it's relatively not congested. But if you were to take and double the amount of perimeter bars you have in that column, so essentially increasing your longitudinal reinforcement ratio by a factor of 2, then you can see things really start to get congested. And if you can imagine beams that are framing into this column, maybe in one direction, or even worse, if you have a beam coming in the other direction, all of that longitudinal steel is going to be passing through that joint, and it could cause you quite a number of headaches when it comes to constructability. So for that reason, if you can do it with 2%, great. There's certain cases where for architectural purposes, the column is limited in cross-section, and you might have to go to something higher than that. And then you'll have to be especially cognizant of the issues that might occur, especially at the joint, and look at that joint carefully to see if there's going to be any congestion problems. Now, ACI 318 does give a minimum number of longitudinal bars that have to be provided in any column section, regardless of load or amount of reinforcement. If you have triangular ties, the minimum number is 3. Rectangular or circular tie column, it's 4. And with spirals, the minimum number of bars is 6, just as a refresher. If you have a rectangular column with rectangular ties, having less than 4 bars obviously doesn't make sense from a lot of different reasons, especially constructability. So what happens sometimes is a confusion between ties and spirals when it comes to circular columns, and this helps us to make sure we don't have to provide any more bars than what we actually need. So once we have an idea of what our column size is going to be, we can determine the exact area of steel that's required for axial force or a combination of axial force and bending. And then we need to select our bars. And this table helps facilitate that. This is the minimum face dimensions in inches of rectangular tied columns. And what this particular table gives you is for a particular bar size and a particular number of bars per face of that rectangular column. This table gives you what is the minimum face dimension of that particular side, which will automatically satisfy all the spacing requirements that are in ACI 318 for detailing of those longitudinal bars. So there's minimum, maximum spacing requirements, and this particular table will help you determine that right away. So if I had some number 11 bars, and it turns out, I'd like to provide maybe 4 or 5 of those on one side, then I would come to the table here and see that I'll need at least a 16 to 20 inch overall face dimension in order to adequately fit those bars while still satisfying all spacing requirements. So this table goes on for other types. We have here bearing type of splice. This is your normal lap splice. Then there's tangential lap splices as well. And the table will automatically give you what that minimum size is in order for the bars to fit in there correctly. So similar to what we showed in our first session, where we had how many bars can fit in one layer of a beam width, this would be equivalent to that. Additionally, there's tables that are available that for circular columns gives you the same information. What's the maximum number of bars you can fit within a certain diameter column while still satisfying all of the ACI 318 requirements for spacing. So tools that will make your life easy. You don't have to keep calculating those spacings all the time, just something to be aware of. So now that we have our column sized and we know what the longitudinal reinforcement is going to be, both the size and the arrangement, we should talk a little bit about tie arrangements and how that has an impact on overall constructability. So you can see three different types of arrangements here. In A, we have a tie that traverses the entire outside dimensions of the column. And we have an interior tie that goes around these four interior bars. If you recall, there's the requirement in ACI 318 where longitudinal bars in a column cannot be spaced more than 6 inches clear. Otherwise, you need to provide some transverse reinforcement to give it those bars lateral support. So what this detail is telling me here is that that spacing is greater than 6 inches clear spacing, so we needed to provide some additional tie. And this is a closed tie. So this is fine. This is a workable solution. What's even better, well, let me tell you first why it's workable. The outer confinement tie acts as a template for the iron worker. Okay, take a look at this one here in A and B, which basically has that same outer confinement tie, whereas in C, you don't have that situation. You have two sets of closed ties that overlap each other. That's not preferred because as we had, it's similar to the case we talked about in our first session where we have a relatively wide beam. We wanted to provide one outer tie that traverses the entire width because then the iron workers can put this directly into the formwork system, center it, and you don't have to worry about basically measuring anything. Whereas if you have something as this configuration is shown here, then that goes away and you have to start measuring to make sure that you're doing the right thing with respect to overall cover and such. Now, why is B preferred over A? It has the same outer confinement tie. Having cross ties, I'm sure it's obvious in this case, having a cross tie like this is much easier to construct than having this closed tie. So they can pop these in very simply, and it's also much easier, as we well know, there's tolerances on all of this location of the longitudinal bars, on the width of the overall tie itself. So being able to get these cross ties around things that are not nice and square, but still in tolerance is much easier than trying to do it with a closed tie. So that's mainly the reason why B is preferred over A. Also, having this outer tie helps prevent the displacement of the longitudinal bars while that cage is being lifted by the crane and set in the formwork. It gives you a much more solid type of construction for that overall cage, whereas this one tends to flex more because of just the overall geometry of how the ties are in that particular cross section. So generally speaking, if you can provide B, that's great. A is fine, but not as preferable as B, and we certainly would want to try to avoid C. A and B is much more easier for the iron worker to complete their tasks in the field than C, and B is even more simpler than A. So this is what we would recommend. You know, your typical details would look something like this on your sheet in the construction documents that show how the ties should be arranged. So this is just, again, very simply how these cross ties go in, 135-degree hook on one end, 90 on the other. What's not shown here is if these longitudinal bars somehow were not perfectly drawn, you know, not perfectly set, and you had to try to get this tie in, it's a lot easier to try to get this type of tie in the section than putting in some type of closed reinforcement. Now here's another cases of tie arrangements. If you have a rectangular column, you can see the diamond shaped tie in A and then our preferred arrangement in B. And I've talked to different iron workers and I've talked to a number of people through the years, and I've asked them about this, and you know, it's almost 50-50 that it really doesn't matter. Some people say, no, I have no issues with the diamond ties. Other people say, yeah, they're more difficult to place, they're more difficult to fabricate. So, you know, having this informal poll through the years, it's also led me to conclude that diamond ties are a little more difficult to fabricate and to place than having your standard cross tie like this. And it makes sense. Once again, you know, if things are not aligned properly in the field, you know, having to try to adjust this and get this diamond tie in is more difficult than just putting in these cross ties. So again, if at all possible, you know, we would try to avoid this in this situation. And looking at this detail again, it's telling me that the clear spacing between the longitudinal bars is greater than 6 inches. So I need those cross ties in order to satisfy the ACI 318 requirements for lateral support of those longitudinal bars. So we've been talking about tolerances through our first session. We're going to continue the discussion here for columns. And what's illustrated on this particular slide are placement tolerance clouds. And what do we mean by clouds? Well, if you go back to ACI 117, the specifications for tolerances in reinforced concrete construction, you can find the information you need there with respect to placement and cover tolerances that would be applicable to this 20 by 20 inch column, 4 number 9 bars and number 4 ties. Okay, so if you go to ACI 117, the placement tolerance is plus or minus a ½ inch. So these bars, these ties can be plus or minus a ½ inch from where the allowable tolerance can be that from where it was originally shown on the drawings. Now there's also a minus ½ inch cover tolerance. So when you take all of these different tolerances into consideration, this blue region that's around the bars are the tolerance clouds where within any of those particular blue regions, that's where the reinforcement can be. So this comes into play, especially at joints where you have beam longitudinal bars coming through, knowing that anywhere within these particular blue clouds, that's where the reinforcement can be. So you see here, we indicate this is the 1.5 inch typical cover that's been specified for this column to the transverse reinforcement, but it can go down to as much as 1 inch based on the cover tolerance that's provided in ACI 117. And then in a similar fashion, these longitudinal bars can be anywhere. So again, we point this out because we're going to show you some examples here of how this could all come into play when looking at the constructability of your typical reinforced concrete columns. So when we take our forming tolerance, when we take a look at our placement tolerances, then we'd like to take a look at our forming tolerances. And if you go to ACI 117, the actual size of the column the permissible tolerance is plus a ½ inch and minus 3/8 of an inch. So if I specified 1'8" for this column, it could be as much as 1'8 1/2 or as small as 1'7 5/8 and be within the allowable tolerances that are given in ACI 117. Now you pair this with the placement tolerances we showed earlier, and then pair it with all the other stuff that's coming through the joint. That will give you a very good idea of if you're going to have an issue or not with the placement of the reinforcement. And that's why we say, try to limit the amount of steel as much as possible. So 4 number 9 bars here is adequate for strength in this particular column, providing more reinforcement longitudinally than what you need is only going to complicate matters in terms of constructability, especially when you consider your placement tolerances and your forming tolerances, how things can get really crowded very quickly if you put in a lot of extra bars that you can satisfy with a smaller number of larger bars. So when we combine those two sets of tolerances, we take our minimum column dimension, okay, and then we take this 17.5 inches. Where does this come from? That comes from our specified column dimension minus 2 times the specified cover dimension plus that ½ inch permissible tolerance. This distance then can go down to a maximum of 17.5 inches. So the smaller, and again, as I had mentioned during our first session, this is the perfect storm of tolerances all happening at the same time. Okay, can it happen? Sure. Does it happen all the time? No, but it's good to be prepared, and try to avert these types of problems before you get the phone call from the construction site. So the actual cover, when you consider the minimum column dimension and the 17.5, which takes into consideration the other tolerance for cover, it can go down to 1 1/16 of an inch for your actual cover. Now our cover tolerance is our specified cover minus that ½ inch that's specified in ACI 117, and that's 1 inch. So we're okay, even in the perfect storm of this particular situation we have in this column. 1/16 of an inch doesn't give you much leeway, to get all of this in there and still be within the allowable tolerances that are given in ACI 117. And this, to show this, is just to, keep in mind, by making things simple, it's even going to be tight. So if you complicate things with more steel than number of pieces than what you need, things can go south very quickly. Now, these hooked bars that occur at the top of a column that gets anchored to the slab at the roof, this is one place that, rest assured, if there's going to be an issue, it's going to occur here. So this is probably a typical detail you would see in a lot of structural drawings where the column bars, this is the same column we were showing before in our previous slides, our 20 by 20 column with 4 number 9 bars and number 4 ties. We're going to anchor those number 9 bars into the slab. Now, where does all this problem come from? Well, it has to do with the placing tolerances and the deviations from elevation. So tolerances can cause us a big problem. So let's start over here on the right-hand side, our allowable deviation from elevation. If you look in ACI 117, you can have a deviation from the actual elevation, the top of this roof slab, of minus 3/4 of an inch. So let's bring the top of the slab down that 3/4 of an inch. That's basically what the cover would be to the bars in the slab. Okay, so that's one thing. The other tolerance we need to concern ourselves with is the slab thickness tolerance, And again, from ACI 117, that's 1/4 of an inch. So again, with the perfect storm of tolerances, we're down 3/4 of an inch. What if the slab comes in 1/4 inch thinner than what was specified? Now we're down a whole inch. Okay, so the bottom of these slab bars coming in and out of the screen is now 1 inch lower, possibly, than what you specified. Now, in addition to that, the rebar fabrication tolerance is plus or minus an inch. And that's the same as if you have a hook bar as shown here or just a straight bar. So these slab bars are down an inch. This rebar can be an inch longer than what they actually are specified to be. So you can see right away, you can have an issue with the hook bars from the column interfering with the bars in the slab. So we'd like to try to head this off before that perfect storm may occur in the field. And how do we typically do that? Well, we can come up with a specified cover and put that on our construction documents and also change that detail a little bit. And then that's going to eliminate a lot of the problems that could possibly occur. So this recommended cover, which would be this cover here to the hook bar, will be some specified cover, which obviously we can't go below the 1.5 inches that's given in ACI 318. So we could take 1.5 inches, add a little for tolerances, whatever you thought might be appropriate. Then we've got the top and bottom bars in the slab that we've got to add to that. And then on top of that, even add another 1/2 inch to account for constructability. And if you provide at least this cover on your drawings, on your typical drawing, on your sheet for column schedule, you're going to alleviate a lot of possible constructability issues in the field. And this is the other thing we recommend. So here's that cover that we have outlined on the previous slide. We also recommend, instead of taking the longitudinal bars in the column and hooking them into the slab, why not splice some loose dowels to those bars? And they can be certainly smaller than the number 9 bars that are in the column. Here we have number 5 bars. We just want to make sure everything gets transferred properly and those bars are anchored properly into the slab. So you can see the benefit of having the loose dowel, that you can have problems eliminated if that perfect storm occurs, where now you could take these loose dowels and move them up or down, whichever way you'd like, and avoid any issues with the slab bars. So providing at least a cover on the drawings and using these loose dowel bars will certainly alleviate any construction problems that you'll have at these very typical locations in a reinforced concrete structure. Okay, let's move on to walls. And we'll start again by looking at preliminary thickness. Unlike some of the other members we covered so far in either of our sessions here, there's a lot of factors that go into selecting a preliminary wall thickness. Now, this could vary, obviously, depending on what structure you have, but these general items need to be considered when selecting a thickness. The length and height of the wall obviously play an important role. Is the wall subjected to both in-plane and out-of-plane loads? So is this a wall on the perimeter of the building that's doing double duty? It's resisting wind forces, both perpendicular and parallel to the face of the wall. And that goes into the third item. Is it part of the lateral force resisting system? If it is, that's where the height of the wall comes into play. If it's a 1-story building and the wall is relatively long, then we know the thickness more than likely is going to be governed by shear. Whereas if it's a multi-story building and it's picking up the lateral forces from wind, generally speaking, that thickness is going to be governed by a combination of axial force and bending. And there's really no good way, unless you have some rules of thumb in your office that you use to come up with the thickness for this. You can certainly start with shear and work from there, and then determine how much longitudinal reinforcement you need in the wall. There are some minimum thicknesses that are given in ACI 318, but those are basically for walls that are designed by the simplified methods to utilize those equations in the code. That's because of the limitations of those methods. Then there's some minimum thickness that are prescribed. So once we have that preliminary thickness, we want to see what else is going on with respect to what's framing into the wall. Now, generally, we may provide some larger bars at the end of the wall, and we would like to confine those. We can call them a boundary element. Now, for special seismic walls, that's a particular designation where, along with that, comes some very special detailing for the transverse reinforcement. But in general, even if it's just resisting wind, we can concentrate some big bars at the end of the wall to resist the wind forces, and then tie those up to provide some good lateral support. So if we need to do that, we want to make sure we have a thick enough wall in order to be able to put those ties in. So that's one consideration. The other consideration is, what if we have some beams that are framing into the end of the wall? And those beams may be carrying just gravity load or whatever the case may be. Now you're talking about having longitudinal bars coming through, and it could be in either direction. So that's something to keep in mind when you're talking about providing a certain thickness to avoid any type of congestion here. And then one other thing to think about is, what if you have, they're designated on this figure here as a link beam, commonly referred to as a coupling beam. So if I have a wall here and maybe another parallel wall here, and I have a coupling beam between them to enhance the overall lateral resistance of my system, you could have diagonal bars, especially in a seismic situation, that may be coming through this joint as well, in addition to the horizontal bars. So taking all of this into consideration with the thickness really is important to do, because this end of the wall can be loaded up with steel very quickly, and maybe you only need, say, a 12-inch wall for strength, but providing a 14 or 16-inch wall may be helpful to alleviate any possible congestion that could occur at the end of the wall. So just something to think about based on what framing you have in this particular case. There is, as we well know, minimum reinforcement prescribed in 318 for both the longitudinal and the transverse reinforcement. For walls that are greater than 10 inches in thickness, you're required to provide 2 layers of such reinforcement. But this is not applicable to basement walls that are single story and cantilever retaining walls. But for a typical building structure, which is not a single story basement wall, you must provide 2 layers of reinforcement in that wall if it's greater than 10 inches in thickness. So what's some good recommendations, guidelines for enhancing constructability? We certainly would recommend using a consistent spacing or multiples of a given spacing to simplify placement of the bars, especially if the cages are going to be built in the field or closely off-site. Okay, this really simplifies matters for the people that are putting these together, using the same bar size if possible at a consistent spacing. People don't have to sort through a whole number of bars to get the correct layout for the wall. Now, this recommendation certainly holds true, and we'll state it and then put another statement right after that. So if you have a wall with 2 layers of reinforcement, it's usually better to locate the vertical bars inside the horizontal bars. Not only does it improve the splice strength and the buckling strength of the vertical bars, it's also a little easier sometimes to construct depending on the situation. But if you do it the other way, where you put the verticals on the outside and the horizontals in the inside, that's fine as well. We just sort of recommend this because we've seen things done in the past where this type of arrangement usually performs a little bit better. Not mandatory though, by any means, especially not ACI 318. So what if the architect decides to put rustications or reveals into a wall or over a segment of the wall? If that rustication occurs over the entire width or at least a large width of the wall, it's fairly simple to handle. You know, we want to provide minimum cover between the inset to our layer of transverse reinforcement. Okay, that's pretty easy to take into consideration, especially if the architectural drawings identify this from the very beginning. Now, if the rustication occurs only over a portion of the wall, then you could start running into some cover issues if not done correctly. There's two solutions here. Solution B, to provide the right cover, is to use these offset or bent bars. That's, as I had mentioned during our first session, that's not one of my favorite things to do. I think it would be best to provide an inner layer of steel and detail this just as if this were an opening in the wall. So have an inner layer that's fully developed on either side of the area of where the rustication occurs. So this one, again, if it's shown on the architectural drawings, you can put this on your typical details, and that'll take care of everything, not having to worry about a reduced cover at the location of where that rustication occurs. Now let's talk about some of our favorite subjects with walls. Intersections. What to do? I've seen just about every possible way you can arrange these things, and I'm taking this information again. I put the source of where this comes from at the bottom of the slide. This one is from the 2009 September issue of Concrete International. There were a number of these detailing, I think it was called detailing corners during the time, where all of really good information from experts in the field who've not only placed the bars, but have worked in the industry for many, many years, coming up with some really good details for all these situations. So when you see a source down at the bottom of that figure, that's where the reference is, and you can go find more information for that. Now, if we have this wall intersection, this L-shaped intersection, we have a single layer of reinforcement in the wall, and we're looking at the transverse, the horizontal bars. The biggest recommendation, and this holds true no matter what type of intersection you have, is don't provide hooks at the end of those horizontal bars. They're really difficult to place, and they're really difficult to handle if you have pre-assembled cages that you're, just imagine dropping that cage down onto that profile and you're coming across these hooks. It's not a very easy thing to construct. So in lieu of using hooks at the ends of the bars, what we recommend, both for these L and T-shaped walls, is having straight bars come in and then have a separate loose bar that hooks around at the same location of the horizontal bars. They get tied to those, and that provides adequate development at the corners. So similar for the L-shaped, you have your T-shaped. Hooking that bar into here is going to cause a lot of problems for construction, and we'd rather have straight bars with this type of L-shaped hooked bar that gets developed properly around the horizontal bars. So this is our recommended. Either one of these two is, well, there's two separate ones here. these two are the recommended ones for L and T-shaped intersections, respectively. Now, when you have two layers of bars, let's look at the case where you have L-shaped intersection. Again, anything that provides especially multiple hooks around the bars at the corners, those are not recommended. Actually, I think the more constructible, if you want to call them, of the two would be D and E from these three recommendations, where again, in D, nothing but horizontal bar, and then you're providing these hook bars that develop everything together. Now, if your wall is thick enough, you can provide these hairpins in either direction. And again, you have nothing but horizontal bar. You know, imagine this cage being dropped in first and this cage being dropped in second. Then you can provide these hairpins that get installed and tied to these pre-assembled cages. And it's a very simple thing to do in the field. Now, you have to have a thick enough wall in order for those hairpins to be developed. But if you do, this can be a very advantageous solution for this type of construction. And you could do something similar when you have two layers of reinforcement. Again, having straight bars come into the intersection and then providing either these separate hooked bars, or if the wall is thick enough, having a hairpin. So we get this question a lot, you know, for the detailing. And like I said, I've seen quite a number of unique and interesting details. And if you follow these time-tested details, more often than not, you're not going to run into any constructability issues. Now, let's continue our discussion with wall intersections. What do you do with the vertical bars that occur at the intersection? And here again, I've seen some really interesting details through the years. And I'm utilizing this reference here from the 2012 Concrete International article because it makes a lot of sense, and it's a very constructible type of detail to provide on your typical details. So when we look at the vertical bars in the wall, we lay it out. Here are the corner bars for the inside face and the outside face. Kind of looks all fine, nice, spaced out evenly. You know, we've got these corner bars here. Once you put the horizontal bars in, that's when you can start seeing where you might run into problems. So these are all color-coded, and they follow the details that we showed previously, what the recommended details are. So we've got horizontal bars that are straight. They're coming into the joint. And then we're providing these hooked green bars and this one outside blue bar to confine the joint. Okay, what we're looking at here is that intersection where the vertical bars are on the outside of the horizontal bars. Similarly, we have the same detail, but the corner bars are located on the inside. Now, when you draw it up, everything looks fine until you consider tolerances, both for placement and fabrication. So we discussed those tolerances here again, and knowing that you could have plus or minus an inch on each of those placing and fabrication tolerances, this corner doesn't look all that great anymore if you consider all of those tolerances. So bars could be stopping at certain locations, and these corner bars, as they're shown, if you have one individual corner bar here, that could be out in space here with no other bars close to it to tie to. And that's also true here. This corner bar, especially here, that could be an issue. And there's things that could happen where, you know, it's a very difficult situation in the field. So in lieu of providing this type of detail, what's recommended is, in this first case here, for the vertical bars on the outside, provide two separate bars which get connected to the horizontal, tied to the horizontal reinforcement that's coming in at that location. You don't need that other bar here that's shown at the corner. So that's eliminated. So that's eliminated. And what we'll provide then is additional bars that are spaced no more than about half of the spacing. Okay, and for the corner, we're going to provide 2 separate bars with a cover of about whatever you specify and another 2 inches to take into consideration tolerances. So that's a very viable solution for this particular situation. Then if you provide this, more than likely you're not going to have any issues with constructability. And something in a similar fashion, if the bars are on the inside of the vertical bars are on the inside of the horizontal bars, put 2 bars within that radius of whatever bend you have, number 5 bar, whatever it may be, and you could take out that other bar that was over here at the corner. It's not doing any good, and then just space the additional bars you provide in the inside at that half of the maximum spacing. And these are constructible. These 2 bars that are shown at the corner in both cases can be adjusted according to how everything is fitting in that particular case. And more often than not, you're not going to get an RFI or any questions about this particular situation. So these are recommended, which have been used for many years and have worked very well. Now let's look at something for a T intersection. And again, looking at the vertical bars, you can see right away that this bar isn't doing anything for us. We could take it out. It's on the interior of this intersection. It's really not providing much of any strength. Once we add the horizontal bars, then we could see issues again. So similar to what we had before, we're going to take this bar out, and then we're going to provide our separate hook bars that tie everything together at the intersection, and then do something very similar to what we had for our first case. A little easier here because we've got a little more to work with. So taking these 2 bars out, providing this typical detail will give you a very constructible intersection when you have a T intersection. Okay, and then this is your final solution. Taking those bars out, having additional bar vertically within that half spacing maximum between the longitudinal bars and the wall. All right, let's move on to wall openings. And what you see here is the trim bars that need to be provided around openings in a wall. Depending on how thick, you're going to need either 1 number 5 at the corners or 2 number 5s. Actually, depending on how many layers of reinforcement it's tied to as well. So this shows a typical layout for those trim bars. Just a couple things we want to mention here. In general, ACI 318 requires that the trim bars need to be developed on either side of the opening. As long as the bars are developed, you don't have to worry about anything else and violate any of the code requirements. What's shown here for this particular opening is a trim bar that goes all the way from the foundation and gets anchored up into either the slab or the wall above. Now that's not such a great detail to provide, and we'll talk about that on our next slide. If this were a large opening that went from the base up to the top of where it's shown here, then it makes sense to anchor that with a dowel bar into the foundation. But for this small opening, it really doesn't make too much sense. You're opening yourself up to some possible constructability issues. So as I had mentioned, 318 does not require these bars to go all the way down to the foundation in situations as shown on the previous slide. As long as they're developed on either side of the opening, we're fine. Now think about the constructability issues with these full height trim bars. What if the exact location of the opening is not available at the time the footing is constructed? So you can have all these dowel bars at where you think it's going to happen, and then it winds up, the opening is even, 6 inches off, and that's going to cause obviously some construction issues. Again, if the opening is moved or its size has changed after the footing is constructed, the dowel bars will be in the wrong location. So that's why it's not recommended to provide these full height trim bars unless absolutely required. So what about developing these trim bars? There's a number of different ways that's done, some more preferable than others. Now, this is usually the preferred method, where you have the corner of the opening and then you measure the development length of the trim bars from that corner. It gives the people in the field a very nice definitive place on how to lay the bars out. Now, some people worry, and duly so, that that opening may not be at the right location or it's moved or shifted. And what other people tend to do is to base the development length of the trim bar on the location of where the first vertical trim bar is around that opening. Then what they do is they make an allowance for position. So they'll allow for cover, tolerances, and the vertical bar spacing, and make that a little bit longer than what the development length has to be. Now that's fine until, the opening again gets shifted. You might wind up with the trim bar that's not fully developed, even based on this method. And finally, there's others who like to take the location of where the last trim bar is and measure the development length from there. And that has its pluses and minuses as well. What if there's a large number of these trim bars? You can wind up with a fairly long development length then that's not needed. So for just, in general, those are your 3 typical ways. Looking at a particular situation, I should say, might give better insight, but having that preferred method, at least from the face of the opening, generally will give you more things to work with respect to satisfying the development length of the trim bars. Now, what about the case where you can possibly have quite a number of trim bars? Now, if this is a fairly large opening and it's intersecting a lot of vertical steel in the wall, ACI 318 requires that half of that reinforcement that gets cut off has to be provided on either side of the opening. Now, if you use the same size bar, you may wind up with quite a number of bars, and then you have to start questioning, are these bars on the outside here really doing anything for us? So what we would recommend in this case, if you find that out, instead of using the same bar size that gets cut, just use some bigger bars. ACI 318 doesn't say you can't do that. All it says is as long as you provide enough steel, they don't care how many bars and that you provide on either side. And it makes a lot more sense in this case than having quite a number of trim bars when you cut a lot of vertical bars in the wall. Then when you have a lot of openings in a wall, then you have to start to think about, is this wall acting more like a wall, or is it acting more like a series of columns and beams? So you may, for certain cases, analyze it both ways and see which way is more critical, and then provide more details for the horizontal portion that acts like a beam, and specific details for the vertical portions that act like a column. So again, just something to think about when you have a situation where there's multiple large openings in the wall. And of course, if that's the case, you have to show special detailings on the structural drawings that indicate what needs to be done in those cases. A typical wall detail wouldn't cut it in this particular case. Now, similar to what we discussed for columns, you have walls that go up to the top slab, and we can anchor and do the same type of reasoning for constructability that we had for columns and provide something similar to that. So finally, in our remaining time we have today, let's go over foundations, and we'll look at both shallow and some deep ones as well. So as you know, ACI 318 requires a minimum amount of interface reinforcement between the supported element, could be a wall or a column shown here, and the footing itself. If the vertical element is subjected to just compression, then we can lap splice the bars in, say, the column with the dowel bars for compression and provide a compression development length. We would carry the dowel bars down to the level of where the footing reinforcement is and tie it. And if it's in compression, we need to develop it in compression, not counting on the length over which the hook acts. ACI 318 does not recognize the hook length with the bend diameter as part of your development length. What's shown here is the bars in tension. So you have a tension development length into the column and a hook development length into the footing. And we can take the entire length down to the bottom of that hook and count that in as our development length. Now, there's cases where if you use too large of a bar here for your interface reinforcement, your dowels, you might not be able to develop it into the footing. So, it's always a balancing act when that occurs. But in any case, this is what the code requires, and we can have some issues here too as well, which we'll talk about very shortly with tolerances. Now, like we showed in this drawing, the dowels go down to the top of the steel in the footing. There's no reason to cut those dowel bars up above. You're going to need extra supports, chairs and such. The best thing to do is bring it down, again, very common sense, bring it down to the level of where the footing bars are, tie it all together nicely, and call it a day. Now, what about dowel arrangements? Okay, there's different ways we can arrange the dowels that are coming out of the foundation and into the column. So on this particular drawing, the vertical bars in the column are the darker circles and the dowel bars are the open circles. Now, A and B are preferred over C for one particular reason. You can see the ties in the column are basically all the same. But the main reason that A and B are preferred over C is because the dowel bars are on the side of where the hooks are, either inside or outside of the hook. Okay, that's the main reason. Imagine the cage from the column coming down on these dowels. It's much easier to adjust these hooks to get everything to fit and have the dowel bars come in, say at 45 degrees and at 90 degrees in the center here, because you can adjust these hooks a lot easier than trying to adjust this leg of the hook of the dowel bar of the transverse bar on this side is much more difficult to adjust than on this side. You can't move this really much, but you can move this to make things fit. And it's for that main reason why we prefer the dowel bars to be on either the inside or the outside of these hooks, just for constructability purposes. A is preferred between A and B because you've got everything on the inside and things are going to go together very nicely in the field. But if you had something like this, for whatever reason you might need to, just make sure those dowel bars are on the hook side and not on the other side of the transverse reinforcement, and everything will go together very nicely. So now let's talk about tolerances, and there's a couple things that we'll cover here. We have this 9'6" by 9'6" spread footing supporting the 18 by 18 inch column, 8 number 6 bars, number 3 ties at 12 inches on center, and we've got 4 number 6 dowel bars going into the footing. We've calculated that we need a 2 foot 0-inch development length of the dowel bars into the column. Now, when we take into consideration tolerances, let's see what might happen to this particular development length. This is another call that you've probably had in the past. You know, the dowels aren't long enough. Okay, they're not sticking far enough out in order to make the proper lap splice length. And this is where it usually comes from. We have a fabrication tolerance on those number 6 dowel bars, as we've talked many times before, for both a straight or a hook bar. According to ACI 117, it's plus or minus 1 inch. We also have a placement or a cover tolerance for the number 6 bars in the footing of minus a ½ inch. Then there's a tolerance with respect to the vertical deviation from the elevation of the top surface of the footing. So that could be as much as a ½ inch or minus 2 inch. So these are our allowables. And finally, after 3 tolerances, we thought we might be done, but we've got this 4th tolerance on the deviation from the foundation thickness. And that's prescribed in ACI 117 is 5% of the footing thickness for a footing of this size. So that's another 1.5 inches. I'm sorry, a 1.2 inch deviation that we need to consider. So when you combine all of those tolerances, the top elevation of the dowel bars can be as much as 4.7 inches below the specified location. So that means the length of the dowel bars above the top of the footing can be 19.3 inches theoretically instead of the specified 24 inches. Now, ACI 117 also gives a tolerance for the length of the reinforcing bar lap splices. It's minus 1 inch for number 6 bars. Now, that's certainly less than almost 5 inches for decrease in the lap splice length. Now, again, keep in mind, this is that perfect storm of all the tolerances being combined at one time, which probably isn't going to happen, but I've seen it where it has happened, where you've got just this little stub of a reinforcing bar sticking up and you're not being able to splice it to anything. So here's where, even though you may have satisfied everything else, you could still run into this problem. And this slide gives you our next one, what it looks like in section. But what you can do in this case is you can, it's a costly solution, but you may not have any other choice but to specify mechanical couplers at the ends of the dowel bars and then provide some new bars, 6 bars, or cut the other, whatever the case may be, and then lap splice those to the column bars to get your required length. There's a lot of creative things you can do. This is just one out of many things to try to remedy this solution, this problem, I should say. And this is what it looks like. So here's all the things in this blue color where you thought you're getting 2 feet, but you really come up with about 19.5 inches. And hopefully, all of those tolerance things don't occur at the same time, but they certainly can. Now, in terms of thickness, we like to provide at least a 12-inch thick footing for constructability. If it's a typical column or wall footing, we don't like to put any shear reinforcement in there, so that can certainly govern everything. When we have a square footing, code permits us to uniformly distribute the bars in both directions. What happens sometimes if you have a wall footing where you don't have much reinforcement, people tend to make a very, very narrow footing, and what they fail to realize is those bars, even if they're like number 4 bars, they have to be developed past this critical section, and you're not going to do it with, say, only a 12-inch wide section. Rectangular footings, the code requires that we take a percentage of the bars parallel to the short direction and concentrate them over the column over the smaller dimension of the footing. Now that's fine, it's certainly doable, but what's even better to do if you can, if you increase the area of reinforcement in the short direction by this ratio, 2 beta over beta plus 1, where beta is the long to short side ratio of the footing, If you increase that area of reinforcement by this ratio, then you can uniformly distribute the bars in that direction, and a lot easier to do in the field. Now let's look at tolerances for footing dimensions and see what we might run across here. This is an 11'6" by 11'6" footing with number 7s at 10 in both directions. We've specified a cover, clear cover to the bar of 3 inches. ACI 117 has an allowable horizontal deviation from the plan dimensions for footings, and for this particular size range, it could be as much as 6 inches or as little as a ½ inch. Our fabricating tolerance for the length of the bar, again, is ±1, and we have a tolerance for the concrete cover of -1/2. So what happens if we have this all come together? We have a minimum acceptable footing dimension then of 11'6" minus the half. So that's 11 foot 5½ inches. We have a maximum acceptable reinforcement bar length. We start out with the 11'6" size of the footing that we specified. We take off 6 inches, so 3-inch cover on either side, and then we add the 1 inch for the tolerance, the fabrication tolerance. So we can have a maximum acceptable according to 117, ACI 117, of 11 feet 1 inches. Our actual cover, if we take off that ½ inch, which is permitted, it's 11 foot 5½ minus the 11 foot 1, divided by 2. So our actual cover could be as small as 2¼ inches, and that 2¼ inches is less than the minimum acceptable of 2½. Now, for 1/4 of an inch, that's up to the licensed design professional to accept that or not. But strictly speaking, it's providing smaller cover than what's required. If you have something along these lines or something even greater, the best way to fix this if it occurs during construction is to make the footing dimensions a little bit bigger. And then you can, sure, it's going to cost a little more concrete, but if you had to go back and refabricate the bars and wait for those bars to come back, it's going to be a lot more costly than providing a little more concrete for the footing itself. Sloped footings. There's a lot of construction issues that you might run across with a sloped footing as opposed to a stepped footing. First of all, you're going to have a trapezoidal shape for the formwork, and that's certainly not standard. So that's a cost right there. You're going to have variable bar lengths. Now, if you recall, during our last session, I showed that elevation of a wall where you could really eliminate this problem by using certain bar lengths and specifying fewer bar lengths than having all the bars come out at a different size. More practically though, you might have some placement or finishing issues. If this slope is great enough, that concrete is going to be tough unless it's a very stiff mix. This is going to go sliding down the slope. So, that's another very practical issue that you may run across. So in lieu of using a slope footing, especially if it's a very steep slope, you should consider using a step footing. And what we have here are some general guidelines you should consider. If the slope of the finished grade is less than 2 feet for a 20 to 30 foot long wall, you could consider just using a standard footing at the lowest elevation. So make the footing horizontal and just use that and carry your wall down to the top of that. Okay, that again, you'd have to do the cost estimates to see what would be more economical in that particular case. If it's a long wall, a step footing will definitely, well, again, definitely, never say never, right? It will most likely be more economical. You try to minimize the number of steps, try to make the horizontal runs about 2 to 4 foot increments so it conforms to standard plywood dimensions or these forming systems that are out there. And you'd like to keep the horizontal runs for at least 10 feet or so, if possible. It all depends on geometry. So what you would have then is something that look like this. We don't recommend a Z-shaped bar for very obvious reasons. You would rather have these L-shaped bars that are much easier to place. So, when you have that situation, it's more than likely going to be better to use a step footing. Mat foundations, another, and this could also, what we talk about here could also go for a podium slab, very similar. We want, this type of system is usually governed by two-way shear. Using the same thickness everywhere, if possible, will also help with constructability and with economy. Try to keep the reinforcement simple. For these very thick mats, minimum shrinkage and temperature reinforcement may govern. What are your layout options? Well, you can have reinforcing bars placed in 2 layers, one at the top and one at the bottom, or for your heavier mats, 4 layers, where there's 2 mats at both the top and bottom of the mat. According to ACI 318 requirements, the bar spacing is limited to 5 times the mat thickness, or 18 inches. So these are all the parameters that we work with. And here are some recommendations. We'd like to try to keep the spacing, especially if you have this double layer of mat, keep them the same in both mats, or keep them such that you space it out every other bar. And the reason for this is, especially if there's a lot of reinforcement, you'd like to keep enough channels open for the concrete to flow very easily into this very, relatively thick mat. We'd also like to keep at least 3 inches clear between the bars for that reason. And also, vibrators have to go in here. So there's a lot of constructability issues that can occur, and spacing the bars as recommended here will help alleviate some of those issues. Now, for a very deep mat, people are going to need to, get down into there and, perform a number of different things. And what's recommended is having some opening in the bars that you can either bundle or double up on. So you can take that into consideration as well if needed. Now, just like a two-way slab, we recommend having uniformly spaced mats, either the 2 or 4 mat arrangement as we showed. Okay, this helps a lot, for constructability. If you need any additional bars, then you provide them where you need them, especially if you have an irregular column layout, which I wanted to show you here. Specify bars on that regular orthogonal grid, and then add bars where required, just as we talked about in our first session for a two-way slab. Now, more often than not, you may not need to develop the top or bottom bars at the end, but if for any case you do, for whatever the situation may be, instead of hooking these bars, which could be fairly significant, number 11 bars is not uncommon in these very thick, heavily reinforced mats. Instead of providing a hook at the end, you can provide this U-shaped bar that will help develop those bars. Now, in lieu of using the hooks, especially for the bigger bars, headed bars work out very well in this case. Similar to what we have, for footing, we want to extend the dowels from the supported column or wall directly onto the bottom mat of the reinforcement, tie down very carefully. And the last 2 items we're going to talk about here, last item I should say, are grade beams. There can be situations, either grade beam or sometimes a pile cap as well, where if the grade beam or pile cap is fairly shallow, you could get some congestion at the intersection of where the supported member and your foundation is coming in. So with this 2-foot deep grade beam, we know that the column or wall bars are going to have to be developed into that grade beam or pile cap. But if it's not deep enough, we may also have to hook the bars from the deep foundation into the grade beam or pile cap. And that could be an issue. You could see all the stuff here. You cut a couple sections here that shows you all the rebar that's here, and that could certainly cause congestion issues at that joint. So there's a couple things we can do. We can, common sense says provide a deeper grade beam so that you don't have to hook the deep foundation bars into the slab and just run them through. If you don't want to spend all that extra material over the entire length of, say, a grade beam, it may not make that big a difference for a pile cap, but for a grade beam it may. You can just deepen the section around where the foundation is to again alleviate the congestion by providing a straight bar from the deep foundation into the grade beam or pile cap. So folks, that basically brings us to the end of our particular session here. As we tried to do in our first session, we tried to present some general recommendations for sizing, for detailing, for tolerances, for, in particular, columns, walls, and foundations, similar to what we did for slabs and beams in the first session. Hopefully, this will be some information you can take back that was useful to you. With that, I will turn it back to Robert to, oh, how could I forget this slide? How could I forget? This is one of my favorite slides. This one, I can't recall where we got this from, but this was one of those situations where constructability was really not thought about very carefully. Now, it looks like there were some considerations for constructability because there's some headed bars here. So they thought they might be running into some issues, with all the hooks and things that are going on here. But unfortunately, that was not enough. So I always like to show this one, not only for, this was perfect for this constructability series, but I try to show it everywhere of what not to do and what can occur if you don't carefully consider what's going on in these reinforced concrete members. So given that, hopefully that picture remains in your head. And now I will turn it over to Robert to see if we have any questions. Robert?
Okay, thank you, David, for that very informative webinar. Audience, please use the question box in the control panel to ask a question for our presenter. We will try to address the questions, as many questions as we can. And David, there are a few questions that we can ask. Going back to, it's actually slide 23, but what it is, it's a column with a hoop, transverse reinforcement, and then you've got the two cross ties that are 135s and 90s. So they're asking that says, is this arrangement type A better in structural performance? And another one says, is having them 90 and 120, 135 opposite end of cross tie, is it relatively efficient? And then another thing that you can maybe address is, would you alternate them as you move up the column? So structural performance, go ahead.
Okay. Yeah, we could certainly address that. Now, in terms of structural performance, it really doesn't make much of a difference. Possibly, in a higher seismic region where you may want those bars to be a little more confined. But even then, we're permitted to use these cross ties as long as they have, the 135-degree hook. And if we're in seismic, it's got to be a seismic hook with a certain length. And as long as we have the 90-degree hook at the other end, there's nothing that really tells us the performance is going to be any different. The main thing of having these is just to ensure that the longitudinal steel doesn't buckle and everything works together as a unit. So it's certainly achieved this way. Now, you could probably tell just by, looking at it, this may give you a little bit more performance, in terms of confinement, but if you don't need it, there's no reason to provide it because this one is going to be a lot easier to construct. Now, in terms of alternating the hooks, the code actually tells us that we need to do this. We don't want to have a plane where all of the 90-degree hooks happen at the same location. And I've seen it where over the height as well, those cross ties are alternated. So I think, did I miss one of the parts, Robert?
No, I think that was
that
great. That was
okay.
great. Let's go to slide 44, and I believe it's a column intersection, a corner, and the attendee asked, why can't you use two blue bars? In other words, probably a 90 on the outside and a 90 on the inside in lieu of the one blue bar and the two green bars.
So in lieu of this one, well, let's go back over here. Is it one of these arrangements that they're talking about?
Yeah, it would be those lower.
This
Um,
D?
yeah, more like D, but trying to, instead of extending those, they're trying to use a corner bar for the inside corner and the outside corner.
I see.
I believe that's what he's.
Okay. Yeah, I mean, I haven't thought it through, but it seems like it would be uh, a reasonable thing to do. Keep in mind, again, think about the tolerances. And, everything looks great on paper, but as you well know, going into the field and having some of these bars shorter than others, it could possibly cause an issue. Like I said, I'm not exactly quite sure what the person is driving at here, but by all means, if you'd like to talk about this some more, just email me here at CRSI or give me a call. And if you sketch it up, and then what I could do is I could also share that with Robert, and he could post that or whatever you think would be appropriate to get the information out, Robert.
Okay, thanks. Okay, it wasn't clear. All right, there's two questions very similar, and I'll phrase it one way. There may not be enough development embedment for either the vertical bar with a hook or even a smaller side dowel with a hook. Cases where this may occur is on the exterior of a building and may require an exterior of a building and may require a column capital. Any suggestions? So the other guy says terminate at the longitudinal column bar in the roof slab. So they're concerned with proper development length of the end bar hook.
So are we talking about that one detail we showed up at the top of the column, this one?
Yeah. So if you're on
So,
exterior, I believe.
okay. So if this were an edge column, and then we have these bars would then be tried to hook into the interior part of the column. And even with a smaller bar, there may have some issues here. Is that what we're?
Yes.
Okay. And what was the, having a capital, I see, or a shear,
Something,
something
yeah.
like this. So, I mean, sure. I mean, anything you have to get creative in these situations, as you well know. And if you need to develop those bars, there's no reason why, adding additional concrete somewhere might be the proper thing to do. What may be an issue is with the contractor convincing them that, but other than that, or even the architect, that's going to mess up their clear space. So that's something, these particulars, that's what makes the job fun, right? Where you have to go in and get creative with what you need to do, and at the same time try to satisfy the architectural program and make sure the contractor doesn't get mad at you.
Oh, all right. On that same slide, another attendee had a question. There's 3 ties shown at the hooked dowels instead of a single tie that you show on slides 29 and 30. So is there a reason
Oh,
for
yes. Yeah.
those ties so closely spaced?
Yes, typically we kind of consider this like a column offset, a bar offset, you know, where you have the bars being spliced to each other. And generally you like to provide at least, this is really not a code requirement. This is more of a recommendation and a guideline, just to make sure, you know, you've got these bars coming in and they're spliced. You want to make sure that you've got enough confinement here where it's transferred. And I would consider it, you know, like a sloping bar where you splice for the longitudinal bars in the column. You know, I know that has a horizontal kick to it from the bar being offset, but if you think of it in a similar fashion, that's a recommendation we have for this type of detail.
Okay, thanks. Audience, realize that we're at the 2:30 Eastern time. It's okay to sign off. However, our speaker said he'd stay on a few more minutes to address the questions that we have still left. So if you want to stay on, that's fine. So we'll go ahead with a few more questions if you don't mind.
Certainly.
Okay, so we've got so I've got a couple questions for this gentleman. Says for SDC D or upper or more, can we place dowel bars in the columns heading toward the footings connection towards the core of the column or the pedestal?
Yes, actually, that's what's required. I can't think of the section number offhand, but those bars do have to, the hooks have to face to the inside part of the confined core. And I
Okay.
could, if you give me a second here, I might be able to, well, I could find that section, but it's in chapter 18 where that provision is given. It's from experiments. They found that having the hooks turn into the central part of the core, it performs better than having them in your typical case where they're oriented away from the central part of the column.
All right. So related to that, a gentleman wants to understand. Can you please repeat what is not recognized in the code for the rebars hooked in the footings in terms of compression and tension forces? That's shown on
Sure,
slide 59.
sure. What the code states is that if these bars are in compression, and let me see, I'm going to try to do this, and I don't know if I'm going to be able to do this or not. Oops. Okay, I somehow got into recording mode, which I didn't want to do, but let me see if I can, no, that's not it. Well, let me just do it with the mouse here. I was going to try to draw a line to illustrate this, but it's not working out as what I was hoping. What the code states is that if you have a hooked bar and that bar is in compression, you cannot go all the way down to the bottom of the hook and count that as part of the development length. Instead, as you know, there's a radius here for this, or a diameter for this bend. You have to take that line above where the bend is and not consider anything below it as contributing to your development length. Okay, I hope that makes sense. It's a code requirement. You have a hook in compression, it's not recognized as being able to be part of the development length of that bar in compression. You have to go above that, the bend diameter above where that hook is. And it's that distance, which would be shorter than that shown here. Say maybe about where I'm drawing this line with the mouse. And from there up to here would be your LDC, your hook part for the, your development length, I should say, for that dowel bar below the top of the footing, which would be less than LDH. I hope that adequately answers it.
I believe so. Thanks for that. All right, you've talked about tolerances and how the members are at different sizes. And the attendee says, do tolerance affect section capacity? Should the engineer check for section capacity in relation to tolerances? Or are the tolerances so small that they really don't make a difference?
Bill, that's a very good question. And basically, ACI 117, if you're within the allowable tolerances that are given in ACI 117, it's safe to say that you don't have to go back and check your structural members for strength or serviceability. Now, given that fact, that's just what the basis of ACI 117 is. If you had, say, for example, a beam that was supporting something that was very sensitive to deflection, then what I would do as I was designing this beam, I might consider, taking into account that, say, decrease in overall beam thickness and calculating my deflections that way. It's not to say you can always go above and beyond the minimum requirements in ACI 318. It's certainly an acceptable, permitted thing to do, and in certain cases, it's warranted. But in terms of anything else, if you're within those tolerances, everything should be fine. You're not going to know about it until it's probably during construction, where you might find out that the tolerances are not satisfied, and that's when you'd have to go back and check. If you, say, for example, had, we'll take that beam example again, where the depth of the beam happens to be a lot shorter than what you designed for, that could have an impact then. And maybe it'll work, maybe it won't. So you might have to come up with a remedy based on what you actually find in the field. My experience with this is, a good inspector will find the big problems. The big problems are the ones you have to really worry about. Typical tolerances, they're close enough to what's in ACI 117. Generally speaking, I wouldn't concern myself with that.
All right, we only got a few more questions. I'll get through a couple more. Person just asked, what's your thoughts on horizontal ties for walls with high axial loads?
I think that person might be referring to the one section in the code where you need to provide those, basically your cross ties. It's a code, all I'm going to say on this is it's a code requirement and it needs to be satisfied. Now you have to be careful, if you have a relatively thin wall, you might not be able to develop those cross ties, and you'll have to, again, maybe have to come up with something creative to either get away from that requirement or to try to satisfy it in some other way.
Okay, a couple more questions. Tenny wants to know, in a shallow grade beam supported by piles, can we bend the reinforcement of the pile reinforcement? I mean, she says means with a 90-degree hook.
Oh yeah, you mean to develop it into the grade beam? Certainly.
Yeah, you have a shallow grade beam. That's fine?
Yeah, it's fine as long as you have enough development length.
Okay. Okay, and then I guess let's end with this one. Is there any guideline to terminate the longitudinal column bars in the roof for a high seismic zone, D or E?
Let me think about that one. I don't recall coming across anything in chapter 18 for that.
Yeah.
Again, if it's part of a special moment frame, I'm assuming you're going to have beams that are going to be up at the top of the building as well. There's not much going on up there, with respect to seismic forces. They're much smaller than what's going down in the first floor. So, providing just a typical detail for constructability will, my best guess would be it should be fine. I can't think of anything.
Okay.
You're going to have a beam there. As long as you develop everything into the beam, it should be fine.
Okay, let's end it with that, David.
Oh, Robert, one thing I want to add to that. What I would do is I would certainly take the transverse reinforcement and carry it all the way up to the top of the beam.
All right. Okay. Well, bring me back toward the end, if you
Oh
wouldn't mind,
yes,
David.
yes,
But
yes,
okay,
yes.
we'll conclude with that. Thank you, Dave, for answering all those questions.
Sure thing.
Audience, please remember to fill out our brief feedback survey that you will see as you exit the webinar. If you're looking for continuing education credit and were unable to join us live for the duration of this webinar, be sure to complete the online quiz at aciuniversity.com. For the following our upcoming webinars, including more webinars in the Constructability series that are happening later this month in September. That concludes today's webinar. Thank you for joining us. We hope you will join us for future learning opportunities. Have a good day.
Thank you, everyone.